Okay, now we start Chapter 2. Chapter 2 is going to start looking at something called kinematics, and we're going to start looking at descriptions of motion. So we're going to take this in pieces here. We're going to look at the description of motion in terms of scalars and vectors, and we're going to look at it in terms of one-dimensional motion. Later on, we will look at two-dimensional motion. This is an area in engineering and in physics that is broadly categorized as dynamics. It's when we start putting things in motion. When we look at things that are fixed, we call it the statics portion. So we're going to look a little bit of dynamics. It's a little more difficult to deal with because we're dealing with lots of parameters: time, distance, acceleration. So we have to take lots of things into account when we look at dynamics and descriptions of motion. It's a branch of physics concerned with the study of motion of an object and the relationship of this motion to such physical concepts as force and mass. So in kinematics, the part of dynamics that describes the motion without regard to its causes. Okay, all we want to know is that something moved from point A to point B. We don't care how it moved, what made it move. We just want to look at and analyze the fact that it moved and by how much. So we're going to look at motion then in one dimension or a straight line. We'll focus then on kinematics and one-dimensional motion. In order to describe the motion of an object, one must be able to specify its positions at all times using some convenient coordinate system and a specified origin. Okay, so we start looking at this by referring to the rectangular or the Cartesian system. Later, when we start doing more in vectors, we'll look at the polar system. The displacement of an object, defined as its change in position, is given by the difference between its final and initial coordinates, or in this case, x final minus I initial. Sometimes that I initial will have what looks like a little 0 or an O down there, x naught. It's the same thing. So when you see x with a little subscript with a 0 or an O, that's x naught, and that just means initial. We write the displacement or the change of position of the object as a displacement. So the definition of a displacement is a delta x, and the 3 bars mean it's by definition x final minus x initial. So in cases where you see that delta x and you have to do a calculation, you are going to substitute x final minus x initial for that relationship. Delta x is positive if x final is greater than x initial, and delta x is negative if x final is less than x initial. So if we look at an example here of a sprinter, if her initial position was at 3 meters, if her final position, x final, was equal to 15 meters, and we take these two values and we plug them into the relationship, delta x is equal to x final minus x initial. 15 meters minus 3 meters is 12 meters. So we have a positive displacement in this case of 12 meters. So what we're going to start looking at and what you need to think of in terms of doing these problems is, are we looking at something called a scalar or are we looking at something called a vector? Okay, the difference between them is a vector is defined by its displacement and typically an angle, where a scalar is not. A scalar is just a number. What kind of numbers are scalars? Pounds are scalars. There's no magnitude or direction associated with pounds. But if we talk about the movement of an object in a specific direction, x, y, or z, and we can identify its direction by a magnitude and an angle, it becomes a vector quantity. So a scalar is a quantity that has a magnitude and no direction. Scalar quantities include mass, temperature, pounds, anything that doesn't give you a direction associated with it. It's specified only by numbers and an appropriate unit. A vector, on the other hand, is a physical quantity that requires the specification of both magnitude and direction. You can typically identify in the text or in your work when you are looking at a vector. It has what's called vector notation. In the textbook, typically it will be in boldface type, and sometimes it'll have a little arrow over the top. Handwritten, we would say that this velocity with the little arrow over it is denoting a velocity vector, where in the next example, acceleration with a little arrow over the top is the acceleration vector. A vector in one dimension notation is not necessary. In one dimension, motion notation is not necessary. There are only two directions in which an object can move. The two directions are indicated by a plus and a minus sign. Okay, remember we're talking about motion in one direction. So typically we're only talking about at this point along the x-axis. If it's one way, it's minus. If it's the other way, it's positive. Okay, so we don't have to put directional information on the unknowns. So example, if a truck moves from an initial position x sub I to 10 meters to x sub f of 80 meters, again we put it into the definition x sub f minus x sub I. Now we have 80 meters minus 10 meters gives us a plus or a positive 70 meters. So we know it's moving along the x-axis, in this case 70 meters. The displacement has a magnitude of 70 meters. The direction is in the positive direction or the plus sign. So at this point we're not dealing with any angles giving us any type of direction. We're using the positive and the negativeness of the number to define its direction. Okay, what if the truck is moving in the opposite direction from an initial position of 80 meters and a final position of 20 meters? So now in this case, when we put the values into their respective places in the definition, x sub f minus x sub I is equal to 20 meters minus 80 meters. Notice now we have a distance or a displacement of minus 60 meters. The direction now is in the negative x direction, as shown by the negative sign. Okay, so now we need to move on to one-dimensional displacement and velocity, looking at vector quantities. So when we look at this, when we come back, we're going to define vector quantities for one-dimensional displacement and velocity.